In this video, we're going to go over work energy theorem. So we're going to connect our unit for work and our unit for energy together. In the first 2 to 3 minutes, we'll learn about the what is this theorem and what is the equation for it. In the next 2 minutes, we will quickly go over step-by-step instruction on how to approach problems that have to do with work energy theorem. This will be especially useful for people that are struggling with understanding how to start a given physics problem, because I'll essentially lay out all the steps for you that will be the same for no matter what problem you encounter in this unit. And in the rest of the video, we'll quickly go over 2 practice problems that have to do with work energy and see how this method applies to solving those types of problems. So if you're struggling with this unit, this is going to be all-in-one comprehensive video that by the end of this, you should walk out with a really good understanding on how to approach these problems. So without further ado, let's start by simply firstly going over what is the work energy theorem. So we learned one of the equations for work, that work is equal to force times displacement times the cosine of the angle between them. However, work has a second equation. Work is also equal to change in energy, so the final energy minus initial energy. The fact that it has 2 equations, right, we can combine them into one and say that this is equal to this. Now, what does this mean conceptually, right? Because in the previous video, we discussed the energy conservation. We said that initial energy is always equal to the final energy. And now I'm saying that basically you can change your energies. Let's consider a simple example. Let's say you're in the car, right? And you have some sort of kinetic energy, right? Because you're driving with some sort of velocity. And you see a red light. You press the brakes and you cause the car come all the way to the stop. So your final energy is actually 0 because you're not moving, so therefore you don't have kinetic energy anymore. But where did all this energy go, right? Shouldn't the energy be conserved? Well, yes, the overall energy between, let's say, the car and the road is conserved, because once you hit the brakes, right, the friction caused the car to stop. So what we can get out of this is that for a given system, you can apply an external force. This is also called non-conservative force. You can apply this force and you can change the energy of the system. For example, like with the car, right? You apply the friction and you take away the kinetic energy from it, right? Now, I didn't lie in the previous video. The overall energy is still conserved. So all the kinetic energy that the car had basically went into the road. So if we take the road and the car together, their energy is conserved. But for the car itself, the energy is not conserved. Another important kind of concept to note here is that work energy theorem provides a link between dynamics, right, or unit of forces, and energy unit, right? The 2 big units in physics essentially are linked together with this equation. That's why it's such an important equation. Now, let's take a look at our step-by-step instruction on how to solve these types of problems that have to do with work energy. Here, we essentially combine our methods for work and our methods for energy. So if you haven't seen those videos, I would advise you watch those. But essentially, right, when we were solving examples for work, we just sketched the free body diagram. We labeled the forces and the direction of the motion. We identified what the angle is, right, between where the object is moving and where the force is applied. And we simply plugged it into this equation, right? Once we found the force, the displacement, and the angle between the two, you can just plug this into this formula. The method for energy was a little bit different because we had to identify what is the initial and what is the final moment in this problem. At each of those moments, right? So let's say you have initial and final moment. At each of those moments, you had to ask yourself 3 questions. Does this object have velocity? If it does, it has kinetic energy. Does this object have height? If it does, it has potential energy. And is there a spring that is being compressed? If so, it has elastic potential energy or the energy of the spring, right? Compressed or stretched. So at any of these initial moments, right, it can either have one type of energy, let's say kinetic, or 2 types of energy, let's say both kinetic and potential, right? So the second part of this method, right, is to basically find the final energy and initial energy and subtract them together and then combine all of this as the third step into one equation, into work energy theorem. So in the next example, we're going to see how these steps are applied to a given problem. So here we have a car with a mass of 1,200 kilograms that is traveling on a flat road at a speed of 25 meters per second. The driver applies the brakes, causing the car to decelerate uniformly due to a constant frictional force. The car comes to a complete stop after traveling for 100 meters, and we have to calculate the coefficient of friction between the car and the road. So let's take a look about how to solve it. So first, let's start with our first equation for work: force times distance times cosine of the angle between them. For this method, right, we always need to draw a free body diagram, even though in this case it's going to be pretty simple because the car is just on a horizontal road. So there's the friction opposite to its motion, the normal force due to it being on the surface, and mg. So the force that is doing the work is the frictional force times the distance. The angle, so let's say if the frictional force is to the left, the car is of course moving to the right. So always the angle between the frictional force and the direction of motion is 180 degrees because friction is pointed opposite to the direction of motion. So this cosine of 180 degrees is -1, cosine of 180. So friction, as you remember, has a force, friction has a formula of mu times n times the distance and a negative in the front. And the normal force, as you can see from this diagram, the normal force is equal to mg, right? So is going to be minus mu times mg times the displacement here. Great. So we took care of the first step, which is solving the work from the first formula. Now let's take a look at the second equation for work, that is equal to final energy minus initial energy. So what is our final and initial moment, right? Our initial moment is when the car is moving, essentially when the car has some sort of velocity. Our final moment is when the car stops. So initially, right, does it have velocity? Well, yes, because we're saying it's moving. So if it has velocity, it has kinetic energy. The car is on a flat road, so there is no potential energy because there's no height and there's no spring in the question. So only kinetic energy. What about the final moment? The car stops, so therefore it has no more kinetic energy. It has no potential energy because again, there's no height and there's no spring that is being compressed. So initial energy is equal to kinetic energy, and the formula for kinetic energy is 1/2 mv squared, and the final energy, right, is equal to 0. So work over here will be final is 0 minus 1/2 mv squared, right? Or we don't have to write this 0. So the third step is putting all of this together. So negative 1/2 mv squared, the change in energy is equal to minus mu mgd, right? I'm simply setting these parts, right, equal to each other, right? That force times distance is equal to change in energy, or as we've written it out here. So if we rearrange this properly, so this becomes positive. Let's see, we're looking for mu. So I can divide both sides by m times g times d. Here we have mv squared over 2. So m times g times d cancels out on both sides. We're canceling out m and g and distance to calculate mu coefficient of friction. On the left hand side, the mass is also going to cancel out, so we can plug in all the unknowns. Velocity, right, is 25 squared. 2 times 9.8 times the distance is 100. So if you plug that into a calculator, you get 0.32 as our final answer. Now, in the next example, we're going to go over another very important example problem of work energy theorem. So But just to highlight overall, right? So we calculated what work is in terms of force, what work is in terms of change in energy, and then combine those two to solve for mu. Okay, in the next example, we have a 4 kilogram block that is initially at rest. So we can say initial velocity is 0 at a height of 4 meters above the horizontal ground. The block compresses the spring with a spring constant of 300 newtons per meter by 0.3 meters. When the block is released from the string, it travels down the hill to the ground and then moves onto a horizontal surface with a coefficient of friction of 0.25. Calculate the distance the block travels before it comes to rest. So let's take a look. So here's a little, we should always basically start with a sketch of the problem, or at least I would advise you do so. So first thing, again, we can start with the work. That work is equal to force times distance times cosine of the angle. In order to calculate for this equation, we always have to do the free body diagram, right? So the work starts over here when the block encounters friction on a horizontal surface. So the free body diagram is going to be the same as in the previous question, right? The friction to the left, opposite to the motion, and gravity downwards and normal force upwards, right? As it is like the force from the horizontal surface. Now, therefore, frictional force, the block is moving to the right. So as always, right, the angle between the direction of motion and the frictional force is 180 degrees. And cosine of 180 degrees is -1. So negative force of friction times D. Force of friction has a formula of mu times N. So just like in the previous problem, right, normal force here is equal to mg. So minus mu times mg times the distance. Great. So this is very similar to the previous example, right? What's going to be different about this problem is the second step, where we find out the final energy and initial energy. So the initial moment here is when it compresses the spring. Let's think about which type of energies will it have at initial moment. And the final moment is when it comes all the way to the stop, right? When the friction causes it to stop. So initially, will it have velocity? Well, no, because it's saying initially at rest. So no velocity, no kinetic energy. Will it have potential energy? Yes, because it has height. So does it have height? Yes, therefore it has potential energy. Is there a spring that is being compressed? Yes, therefore, right, it's compressed by 2. So therefore there is elastic potential energy. What about the final moment? So let me write this out. Initial moment, initial energy, right, is equal to potential energy plus elastic potential energy. Let me plug in for the formulas of those. So potential energy is mgh and elastic potential energy is 1/2 k delta x squared. What about the final moment, right? So the final moment is, does it have velocity? No, because the block is coming to the rest. Does it have height? No, because the block is on the ground, so no potential energy. Is there a spring that is being compressed? No, therefore the final moment, the block has energy of 0. There's no types of energies essentially. So the final energy is 0. In other words, the work, which is final energy minus initial energy, is just going to be final 0 minus initial, that is mg plus 1/2 k delta x squared. So just like in the previous question, right, we're setting those two equations equal to each other, but now solving and rearranging this for distance. So negative mgh plus 1/2 k delta x squared, we're almost done, is equal to mu mgd. Of course, the negative can just cancel out from both sides. And we're rearranging for distance. So let's divide both sides by mg, by mu mg, right? In order to rearrange it, mu mg. So now we have our final formula for distance. We just have to plug in all the numbers. So mass is 4 kilograms times 9.8 times the height of 4 plus 1/2 times 300 for k, delta x 0.3 squared, mu 0.25, m is 4 kilograms, g is 9.8. So if you plug all of that in the calculator, you should have a distance of 17.4 meters. Great. So in the next video, we're going to go over next topics for physics, which is going to be momentum. Keep practicing and make sure that you do some practice on your own to make sure that you understand this unit. You can even try to rework these examples on your own to see if you really understand it. Remember, the best ways to learn is to, after watching somebody explain it to you, to practice by yourself. So keep watching these videos, keep practicing on your way to an A. Thank you guys for watching.